All right, so today we're going to talk about Lewis structures and get into some types of bonds. To answer the essential question, how can we identify types of bonds and represent them with Lewis structures? All right, so to start out, Lewis structures are just a representation, a drawing of an atom or molecule's valence electrons. So where are they and what are they doing? Okay. So if we wanted to represent something like oxygen and its valence electrons, okay, it's in group 16, so it should have 6 valence electrons. And the way that we draw them is we just go around clockwise, all right, and just put down those valence electrons, okay? Now you'll notice some of these valence electrons are paired, all right, so these are two, we call them lone pairs, all right, because they're alone together. And then we have unpaired electrons. These ones are ones that can participate in bonds. They can be traded, lost, stolen, shared, etc. If we wanted to do nitrogen, nitrogen is in group 15, so it should have 5 valence electrons. 1, 2, 3, 4, 5. All right. This one has 1 lone pair and 3 unpaired electrons. Then for something like carbon, all right, carbon has 4 valence electrons. It's in group 14, so it's got 4. All right. And we can do those 4 like that. So carbon has actually 4 unpaired electrons, which means it can do a lot of bonding, right? So if we're going to just summarize that, lone pair electrons, all right, so these paired ones don't typically participate in bonding. They're usually just fine the way they are. They like to be alone. Single electrons can participate in bonding. So carbon has the most ability to participate in bonding because it has 4, nitrogen with 3, oxygen with 2. So again, those lone pairs are these ones that are paired up together, and then these single electrons, these unpaired electrons, are the ones that can participate in that bonding. So when we talk about bonds, these are just forces that hold atoms together in a chemical compound. The 4 main types we'll talk about are ionic bonds. This is when electrons are transferred from one element to the other. And we get a cation for the element that lost an electron, it's positively charged. And we get an anion for the element that received the electrons, it gets a negative charge. After this exchange, one atom has got that positive charge and attracts to that negatively charged anion. The next type of bond we'll talk about is covalent bonds. Co meaning together, and valent referring to valence electrons. So covalent means putting your electrons together, which makes sense when we read the definition. It's a strong bond where electrons are shared. And we get 2 types. Polar covalent bonds, where electrons are shared unequally, and non-polar covalent bonds, where electrons are shared equally. So you can think of this sort of like if you have a friend or a family member that you share things with, all right, the sharing isn't always equal. Sometimes somebody gets more turns or more time with the thing that you are sharing. Same thing here with atoms. Sometimes one atom gets more time with the electrons than the other. The last type of bond is metallic bonds. This occurs between 2 metals, and the electrons of both elements are delocalized, which is a fancy word for spread out, dispersed. And these electrons can flow freely. They're not tied down to one particular atom. So, if we're going to dive into ionic bonds, all right, they happen between a nonmetal and a metal, and an electron is transferred from one element to the other, and our resulting ions will attract. So this is again between a metal and a nonmetal. The nonmetal has a really high electronegativity, and the metal has a low electronegativity. So this means electrons are transferred from the metal to the nonmetal. So in this case, our electron gets transferred. And after this transfer occurs, all right, we now have the nonmetal has collected that electron. The metal has lost that electron, meaning we have that cation and anion, and these oppositely charged particles attract together. They're pulled together by Coulomb's law. If we move forward, right, we get to polar covalent bonds. So these are the unequal sharing. This happens between 2 nonmetals, right? And the term polar comes from the molecule having two poles, right? Sort of like the Earth has a south pole and a north pole, which are oppositely charged. Molecules can also have a north and south pole, but we call these the partial positive pole and the partial negative pole. I've color-coded it so the positive end is slightly blue and the negative end is slightly red because there is an unequal sharing. One atom gets more time with the electrons than the other, and you can sort of see it like the electrons tend to be more around this nonmetal over this nonmetal atom. So again, this is a strong bond where electrons are shared. In this case, the polar covalent bond, the electrons are shared unequally, resulting in positive and negative poles, kind of like the Earth has a north and south pole. So this forms from two nonmetals. In this case, one nonmetal has a really high electronegativity and it gets more turns with the electrons. Remembering that electronegativity is the ability of an atom to attract electrons, right? So one nonmetal has a really good ability of attracting electrons and one kind of sucks at it, right? So in this tug of war over the electrons, the more electronegative element becomes negatively charged because it has more turns with the electrons. We represent this partial charge with this symbol here, delta minus. It's a lowercase delta, it's a Greek letter. And this is read as partial negative. So not full negative charge like ions, but partially negative, because there is some sharing going on. The other nonmetal has got a medium electronegativity, so it gets fewer turns with the electrons. It's not so low that it completely loses the electrons, but it's not high enough to share equally. And so we get that partial positive pole represented with the symbol partial positive. As we move further on, all right, we can get that non-polar covalent bond. In this non-polar covalent bond, the electrons are shared equally. Okay. This forms, again, between a nonmetal and a nonmetal. And in this case, neither nonmetal is significantly more electronegative than the other. You can think of this like a game of tug of war where the two teams are equal strength. Nobody is really winning. Both of these atoms get pretty even turns with the electrons. They spend some time around one atom, some time around the other atom. And so neither atom has any charge. The electrons aren't gathered on one side or the other, so there's no negative and positive charges to talk about here. The last one we'll talk about here is metallic bonds, which, as you may have guessed, happens when a metal combines with another metal. And in this case, electrons of both elements are delocalized, they're spread out, and can move freely. So again, between a metal and a metal, the reason why they spread out so much is because both metals have such low electronegativity that these electrons are not strongly attracted to either of these atoms and can kind of move more freely. Since electronegativity is the ability of an atom to attract electrons, to pull them towards itself, if electronegativity of both atoms is really low, the electrons can spend a lot of time being out in the open. And we sometimes refer to this in chemistry as a sea of electrons, kind of like the ocean has waves and the water moves kind of wherever. It just flows, it flows. It's not really stuck in one place. In this case, same thing. Electrons aren't stuck in one place. They can flow sort of wherever they want throughout a metal. And this is why we do make wires out of metal, because they can conduct electrons, conduct electricity. Electrons can move freely through them without getting grabbed and attracted by a high electronegativity atom. So besides talking about the types of atoms involved, like metals, nonmetals, we can also talk about the electronegativity, which is something that we did mention. So we can identify bonds either by whether they are metals and nonmetals, metals and metals, or nonmetals and nonmetals. But we can also identify it here using the difference in electronegativity between the atoms. So for our nonpolar covalent bonds, both atoms have a very similar electronegativity, so the difference between them is very low. So if we're trying to identify these bonds, we can subtract the electronegativities of the two atoms and compare using this graphic. All right? I will not make you memorize this. If the difference between the two electronegativities is 0.4 or less, we tend to call it nonpolar covalent. The electrons are shared pretty equally. If the difference between them is between 0.4 and 2.0, we call them polar covalent. The electrons are shared somewhat unequally. One atom gets more turns with the electrons. And if the electronegativity difference is 2.0 or more, one of these atoms is so electronegative that the electrons get transferred instead of shared. All right, so to get a better idea of what's actually going on with the different types of bonds, I'm going to use these models here to sort of show you what's going on. So if we're talking about O2, the molecule O2, we have an oxygen atom bound with an oxygen atom. If we check their electronegativities over here, oxygen has an electronegativity of 3.44. So one oxygen has a 3.44 electronegativity, the other also has a 3.44 electronegativity. If we subtract the two, we get an electronegativity difference of exactly 0. So we would say that electrons are perfectly evenly shared between these oxygen atoms, which should make sense because they have the exact same electronegativity. One atom is not getting more turns with the electrons than the other. So that's why it's non-polar covalent. Now, we can have a small amount of difference in electronegativity. All right, so now we've moved up to a slightly higher difference in electronegativity for a molecule like methane. Carbon has an electronegativity of 2.55, and hydrogen, all right, hydrogen has an electronegativity of 2.2. So the bond between carbon and hydrogen has an electronegativity difference of 0.35. Right. So if we're looking at the way the electrons are shared in this atom, right, this green region indicates that there's not a lot of charge. It's mostly neutral. So we end up with non-polar covalent again. Now, if we get a little bit more difference in electronegativity here, all right, we've moved into the polar covalent range. The molecule HBr has a hydrogen atom with a 2.2 electronegativity and a bromine atom with a 2.96 electronegativity. When we subtract the two, we get a difference of 0.76, which means we are in the polar covalent range. We're more than 0.4, but we're not quite in the ionic range. We're less than 2.0. And we can start to see there is a region of blue positive charge and a region of yellowish getting towards reddish negative charge. So this molecule has some polarity to it. Now, as we increase that difference even more, we look at a molecule like water, all right, H2O. Hydrogen has an electronegativity of 2.2, and oxygen has an electronegativity of 3.44. So oxygen is much stronger. The electronegativity difference is 1.24 when we subtract these two. So we're still solidly in the polar covalent range, but now we're even more polar. You can see there is a much higher negative charge. It's like fully red up here, compared to these hydrogens, which have this pretty strong blue positive charge to them. All right? So we now have these partial charges located pretty distinctly between the two atoms, with the more electronegative atom being negative, that is oxygen, and the less electronegative atom, in this case you could say electropositive, being hydrogen. So that's how we end up with this polar covalent bond, more polar than this previous atom. It's got much stronger poles to it. Okay? So if we wanted to summarize all of this information in a table, all right, ionic bonds happen between a metal and a nonmetal. Electrons in this case are transferred from the metal to the nonmetal. We get positive charges and negative charges, and this happens between atoms of high and low electronegativity. The high electronegativity atom has a much better ability of taking electrons compared to the low electronegativity atom. That's why they're transferred. The polar covalent bond and the nonpolar covalent bond both happen between nonmetals. In one case, electrons are shared unequally, and the other case, electrons are shared equally. With the unequal example, we get a partial positive charge, all right, a positive pole, if you will, hence the name polar. It's got poles, just like the Earth has poles, north and south. So partial positive and a partial negative charge. This happens when the nonmetal has a high electronegativity bonds with one that has a medium-ish electronegativity. So there's some difference, but not a lot. The nonpolar covalent bond happens when electrons are shared equally. There are no charges, no partial charges, because both atoms get even turns with the electrons. One isn't more negative than the other. So this can happen between two high electronegativity nonmetals or two medium-ish electronegativity nonmetals. Last piece here, the metallic bond happens between two metals. Electrons are delocalized, spread out in a wide area. there are no charges to speak of, and this happens between two low electronegativity atoms. Neither one has a very strong pull for electrons, so they can flow freely in this sea of electrons, if you will. And that is all. I've left you this little Valentine's Day joke. All right, so covalent bonds happen when there's a sharing of electrons. So the joke is, would you be my co-Valentine? Which a student did tell to me, and I loved it, so here it is. Checkpoint quiz when you're ready.